Now I am going to explain the problems which are related to half-wave rectifier. I am Dr. B. Ravi Kumar, Associate Professor, Department of EC, Institute of Aeronautical Engineering. As we come to the problems on half-wave rectifier, we know that rectifier and types of rectifiers. Rectifier is an electronic circuit which converts an AC input signal into pulsating DC output signal. There are basically two types of rectifiers, half-wave and full-wave rectifiers. And full-wave rectifier can be further divided into full-wave rectifier, center-tap full-wave rectifier, and bridge rectifier. As we know that these rectifiers, when we move from half-wave rectifier to full-wave rectifier and bridge rectifier, so the half-wave rectifier, some parameters which help us to characterizing of these rectifiers, whether it is good or not. Half-wave rectifier, how it is good, by following some characteristic parameters. These parameters like DC voltage, RMS voltage of the rectifier output, and ripple factor, efficiency, peak inverse voltage, frequency, output frequency. So this peak factor, form factor, all these parameters will help to say that whether that a particular rectifier, the required rectifier, the given rectifier is efficient or efficient to convert the AC into pulsating DC signal. Simply we can say that half-wave rectifier is not at all practically at all useful, because it has only 40% efficiency and the ripple factor is more than 100%. So it's not possible. It's not preferable for practical applications. We move to a full-wave rectifier and then bridge rectifier. So anyway, now we will see now find out some solve problems on half-wave rectifier. Consider some problem. Let us see here this problem. When we see this problem, so this half-wave rectifier is used to supply 24 volts DC to a resistance load of 500 ohm, and the diode has a forward resistance of 50 ohms. Calculate the maximum value of the AC voltage required at the input. This like given the problem has given of the DC delivered DC voltage and load resistors and its internal forward resistance of the diode. Then what would be the voltage applied to get this 24 volts? So first of all, whatever we have given the problem, and read that problem and write down the given data. So here it is, all the parameters of the half-wave rectifiers are given. So given data, before going to take the given data, just remind us, recollect some of the formulas which are helpful to find out these problems. So first one is VDC, the DC voltage in half-wave rectifier. How to measure the DC voltage in half-wave rectified output? So there are some mathematical equations. With help of those mathematical equations, we derived that DC voltage. Finally, we got that VDC is equal to maximum voltage Vm by pi. And if we consider that diode forward resistance, secondary coil resistance, and load resistor, so if you consider that kind of parameters, so it is not exactly, the VDC is not simply Vm by pi, it is Vm by pi subtracted by that drop across the forward resistance of the diode. If you include load resistance of the diode, if you include secondary coil, so because both all are in series. If you see this diagram, this is the primary coil of the transformer and this is the secondary coil of the transformer and this is the diode. This is the load resistor. Okay. So if the load resistor, if secondary coil has some internal resistance, assume that it has internal resistance. When we consider that internal resistance, it is like a small resistor across here, and a forward resistance has internal resistance. So when we consider this is like RF and a load resistor. This RS, RF, RL both are in series when current I flowing through the network. So by considering these three parameters RS, RF and RL, so that VDC is not simply Vm by pi, we can consider this RF plus RS something. So Vm by pi minus IDC into RF. If we consider the secondary coil resistance, we add this one RF plus RS. So likewise, by subtracting of the drop across this source secondary coil resistance and forward diode resistance, then we can drop that value from Vm by pi. VRMS also calculated. So we derived from this mathematical equation of the rectified output. So from the definition VRMS, so we will get Vm by 2 and ripple factor gamma. So gamma actually we taken from this VRMS by VDC whole square minus 1. By substituting this VRMS by VDC whole square minus 1, you will get the ripple factor. That ripple factor value, when we substitute all the required parameters, then we get 1.21. And efficiency, basically efficiency is nothing but the DC power delivered by the particular rectifier divided by the AC input power given to that particular rectifier. Here if it is half-wave rectifier, the PDC by PAC, the PDC is derived from the VDC square by RL, and PAC like which derived from VRMS square by RL. Then we substitute into this efficiency, we will get 40.6%. So peak inverse voltage. So what is the maximum peak inverse voltage in the half-wave rectifier is like it is a Vm. When the diodes are in a reverse bias, what is the maximum voltage reverse voltage across that particular diode is Vm. And frequency, output frequency. So this output frequency Fi, why it is called Fi means we know that the half-wave rectifier input is sine wave given to the rectifier. You will get a rectified output half wave and negative cycle gets cut off, and only positive cycles need to be gets accepted or passed through the diode. Then only one cycle is appeared across the load, and the remaining cycle gets off, zero voltage across the load. So this output, when we see that when we measure the frequency of time period, the time period is nothing but one full cycle, positive and half negative cycle. Here also the output is one half cycle and 0 cycle. So here also the time period is same, capital T. Here it is capital T. So when T is same, frequency is also same. But the rectified output which is equal to rectified frequency F naught is equal to output frequency is equal to Fi only, because we consider both cycles. So that is frequency in the half-wave rectifier. Now let us consider, by remembering all these parameters, by recollecting all these performance characteristic parameters, and then do this problem. So the immediate step need to take is that what is given data? Note down that given data of a given problem. The given data for the above set problem is half-wave rectifier is used to supply 24 volt DC to the resistance load. So the rectifier, half-wave rectifier, so as already given 24 volts delivered to the load. So VDC voltage, they have given VDC is equal to 24 volts across load. And load resistor is RL is equal to RL is equal to 500 ohms. And diode forward resistance RF is equal to diode forward resistance RF is equal to 50 ohms. And then calculate the maximum AC voltage, like maximum value of the AC voltage, nothing but Vm is equal to what? So we know that formula basically for half wave rectifier. If it is half wave rectifier, that VDC is equal to Vm by pi for neglecting all the forward resistance of the diode and the secondary coil diode. If we consider that the resistance of the internal resistance of diode, forward resistance of the diode, then we need to subtract that drop across the diode. So because it satisfies the KVL also. So drop that voltage across forward resistance measured by IDC into RF. IDC into forward resistance RF. So in this problem, it has not given that secondary coil resistance. Only we can consider minus IDC into RF. And then we don't know IDC. How to find out IDC? First I find out the IDC. Find out the IDC. Because find out the IDC, it is multiplied by RF. And then we have a VDC, we have pi. Then we'll get PM. Okay, right. So first we need to find out the IDC. What is IDC? Basically the half wave rectifier. The output of the half wave rectifier just passing from the diode. When it is conducting, diode is conducting, the current flowing in the RL, then the voltage across measure with the RL is nothing but VL or VDC. So here then IDC is equal to voltage across RL in the half wave rectifier is VDC, already is given in the problem that voltage DC voltage across load resistance, VDC by RL. VDC by R. So we will get that VDC 24 volts VDC divided by 500. The 24 divided by 500, we will get 48 milliampere. 48 milliampere. IDC is equal to 48 milliamperes. So here, well, we know that IDC is equal to 48 milliampere. Then IDC into RF is equal to 48 milliamperes into RF. RF is equal to what? We know that forward resistance RF is equal to 50 ohms. 50 ohms. So when we see this, this one, 48 into 50, 2400 minus 3 means 2.2.4 2.4. This 2.4 substitute in this actual formula. So we take this formula. VDC is equal to Vm by pi minus IDC into RF. But we want Vm. So rearrange this equation. VDC plus IDC into RF is equal to Vm by pi. And Vm is equal to pi into VDC plus IDC into RF. We know already IDC into RF value is 2.4 and VDC is equal to 24. So pi into 26.4. So when we calculate pi into 26.4, 26.4 into pi, 82.93. So Vm is equal to 82.93 volts. This is the way we find the maximum voltage required at the input. So when we provide 82.93 volts to the half-wave rectifier, it will deliver to the load DC voltage across the 500 ohm resistance is equal to 24 volts. So the problem is given in the reverse order. So 24 volt delivered to the load across 500 ohm by providing the internal resistance of the diode 50 ohm. What would be the maximum Vm voltage required to provide at the input of half-wave rectifier? We will get 82.93. In this way, we will get input voltage. So simply by considering VDC 24, RL 500 ohm, RF 50, find out the Vm. We have a formula VDC is equal Vm by pi minus IDC RF. As I told, minus IDC RF when we consider that forward internal resistance. Otherwise, we simply Vm by pi only. So, but here VDC is given, pi already is a constant. So take that Vm. So extract that Vm with all the parameters, then you will substitute, you will get 82.93. Next, let us see problem with all the parameters related to transformer, second transformer and load resistors, and find out all the performance characteristics of the rectifier, half-wave rectifier. Let us consider, we'll assume that it is a half-wave rectifier. Half-wave rectifier. This half-wave rectifier, all these concepts like now we will take from the question bank. In our website, we have a question bank. Take this problem from the question bank. So, what is the given data first? Once we note down that given data, it is very easy to find out the problem. So, the given data, a 230 volts, 550 Hz volts is applied to the primary of a 4:1 step down transformer used in a half-wave rectifier having a load resistance of 600 ohm. Assume that the diodes to be idle. Determine DC voltage, DC output voltage, DC power delivered to the load, peak inverse voltage, and output frequency. So the problem, given problem. So and also the diagram, we know that the primary coil. If it is step down, the secondary coil is winding is very less. Okay, and then diode and load resistor. The voltage measure across this load resistor. Output voltage or DC voltage. So this is RL. So this primary coil, the coil is like a 4:1 ratio. So 4 times 4 windings turns coils ratio for at a primary 1 with respect to 1 and the secondary. So 4:1 turns ratio. Input is 230 volts. The input primary voltage is 230 volts. And if it is a signal is given is AC signal, we will consider that frequency 50 Hz. At 50 Hz frequency. So input voltage. Now I just consider this here. Basically, to avoid the confusion of primary voltage and secondary voltage. Now I am consider that primary voltage as like V1 RMS or simply V1. Always AC signal is measured in RMS. So V1 is equal to 230 volts. We don't know secondary coil, but they have given turns ratio. N1 is to N2 is equal to 4 is to 1. And what is secondary coil voltage? Okay, no, given data, right? Write down the given data first. And load resistor RL is equal to 600 ohms. Assume diode is to be idle, and find out the DC voltage and DC power delivered to the load, PDC, and peak inverse voltage and output frequency. If you want to know, we will find out triple factor also. So first, we will take that. In order to find out this VDC, PDC, peak inverse voltage, the primary factor need to be applied is DC voltage. VDC is equal to Vm by pi. So means we need Vm. How to get Vm? This Vm extracted from the VRMS. So Vm is equal to actually this one VRMS is equal Vm is taken from we can take this Vm is equal to secondary coil voltage V2 RMS is equal to, we have a formula, right? So then we'll take that one. Okay. V2 RMS is equal to N2 by N1 into V1 RMS. So what we find out here it is N2 by N1. We know that N2 is secondary coil turns ratio and N1 is primary coil turns ratio. So N2 is nothing but 1, N1 is nothing but 4 into V1 RMS. When V1 RMS is equal to V1 RMS is equal to V1 of RMS is nothing but 230 volts. 230 volts. Okay. So here it is 1 by 4 into 230 volts. We'll get a 57.5 volts. This is what V2 secondary coil voltage. So when we have a V2 57.5, what is Vm? Vm is equal to, one second, I will take another color. Vm is equal to basically the formula Vm is equal to 2 into V2 RMS. We know the secondary coil voltage V2 and we want to Vm is equal to 2 into V2 RMS. So we just now we find V2 RMS secondary coil voltage root 2 into 57.5, then we will get that 81.31 as a Vm. Once we find out the Vm, then we can apply this Vm into VDC and PDC, like ripple factor, everything. So now substitute VDC. VDC is equal to Vm by pi. What is Vm by pi? Vm by pi 81.31. 81.31 divided by pi is equal to, you will get 25.89. you get 25.89. So this is about VDC. Then PDC is equal to, you know that DC power delivered to the load is nothing but VDC square by RL. VDC square by RL. We know the VDC 25.89 whole square divided by RL is nothing but 600 ohms. You will get the answer 1.11 watts. And then next one is, for example, this one is A, this one is B. Next, C is equal to peak inverse voltage. In half-wave rectifier, peak inverse voltage is nothing but maximum voltage of the secondary coil VM. So the peak inverse voltage is VM. We get that VM is equal to 81 point. VM is equal to 81.31. And then frequency, output frequency, F0 is equal to F5. Already in the problem is given the frequency is 50 Hz. So F0 is equal to 50 Hz. Suppose if you want to find out a ripple factor, so this simply we can find out ripple factor VDC by VRMS whole square minus 1. Then you will get around ripple factor will approximately will get 1.21. Likewise, we'll find out the problem. So in this problem, the given data is all the parameters in the rectifier, input primary voltage, primary signal frequency, and turns ratio. And the immediate step to find out is the secondary coil voltage in terms secondary coil voltage in terms of primary voltage and the turns ratio. We'll get V2. Once we know the secondary coil voltage, like secondary voltage in RMS, then we find out maximum voltage across secondary coil is VM, root 2 into VRMS. So then once we get that VM, then directly we can substitute all the parameters in the VDC, PDC, peak inverse voltage, so and ripple factor, everything. So this way we find out the problems in the half-wave rectifier. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.